Let's talk about separable equations. This table shows the temperature of a turkey in a 350-degree oven. These are actual data. I took these measurements a while back. 142 degrees at 4:38, 153 degrees at 5:09. Use Newton's law of cooling to determine when the turkey will reach 160 degrees. All the books say you should cook it to 165, but I think it's kind of dry at 165. I don't think I'm playing it too dangerous like by cooking it to 160. Newton's law of cooling. The rate at which the temperature of an object changes is proportional to the temperature difference between the object and its environment. First, let's express this as a differential equation. Okay? So T is going to be the temperature of the object, and E is going to be the temperature of the environment. The rate at which the temperature of an object changes, that's going to be dT dt, the rate at which the temperature changes. It's proportional to the temperature difference between the object and its environment. In other words, it's some constant K times the difference between the temperature and the environment. So it's K times T minus E. In this particular case, since the temperature of the environment is 350 degrees, that's how hot it is in the oven, we have dT dt equals K times T minus 350. Now let's solve the differential equation. A first-order differential equation is separable if it could be written in this form. dy dx equals some function of x times some function of y. We call it separable because then we can separate it into a function of x and a function of y. Examples would be dy dx equals 2x squared times y cubed, or dy dx equals 5x times 5x over 1 minus y squared, because then you could write that as 5x times the quantity 1 over 1 plus y squared. Also, dy dx equals y squared. Now, why would dy dx equals y squared be a separable differential equation? Well, you can think of the function of x as being 1. That's a function of x. Here's how we'd solve a separable differential equation. So again, we start off with dy dx equals g of x times phi of y. Let's get the phi of y on the other side, okay? So we'd have, and then let's get the dx on the other side. I know it seems cheesy to multiply both sides by dx, but it works. So we have 1 over phi of y dy equals g of x dx. So let's say 1 over phi of y is f of y. And since 1 over phi of y is f of y, we can write the whole equation as f of y dy equals g of x dx. Now we integrate both sides. We have f of y dy equals g of x dx, and that would be our solution. If required, we could solve for y in terms of x. Sometimes we don't need to do that. Okay, now let's solve the initial value problem. I know this first problem is complicated, but it's a real problem, not some bogus, goofy problem that textbook authors sometimes create. So here's our differential equation. dt dt equals k times t minus 350. This is a separable differential equation. So notice this is our function of little t, and this is our function of capital T. We also have t of 0 equals 142 at time t equals 0. Time t equals 0 is going to correspond to 438. It's 142 degrees. And we have t of 31 equals 153. That just means that 31 minutes later, at 5:09, it's 153 degrees. Okay, so again, let's separate this differential equation. Let's move the t minus 350 to the other side and move the t, little t, onto the right side. So we have 1 over t minus 350 dt equals k times d little t. We've separated it. Let's integrate. So we have the integral of 1 over t minus 350 dt equals integral of k dt. The antiderivative of the left side is just going to be the natural log of the absolute value of t minus 350, and the antiderivative of k is just kt plus some constant c. Okay, we're going to write the absolute value of t minus 350 as simply 350 minus t. Why? Because the absolute value of t minus 350 is 350 minus t, since capital T is less than 350. Capital T is less than 350. So what's inside the absolute value signs is negative. So the absolute value of t minus 350 is 350 minus t. The temperature of the turkey is definitely less than 350 degrees. Okay, so we have this as our solution. We need to plug in initial values to find c and k. We had t of 0 equals 142, t of 31 equals 153. So first, let's plug in t of 0 equals 142. You plug in 142 for t in this equation. and you get natural log of 350 minus 142 equals c. Notice that the little t is 0, so it's just going to drop out, so the right side is c. This simplifies to 208. So we have c equals the natural log of 208. That's great. So this equation I've circled at the top is now the natural log of 350 minus t equals kt plus the natural log of 208. Now let's find k. So again, we start off with this solution. T of 31 equals 153. Plug in little t equals 31 and capital T equals 153. And we end up with the natural log of 350 minus 153 equals 31k plus natural log of 208. Okay, let's solve for k. So 350 minus 153 is 197. We have natural log of 197 equals 31k plus natural log of 208. Subtract natural log of 208 from both sides, and we have 31k equals natural log of 197 minus natural log of 208. Let's divide both sides by 31. And we have k equals the natural log of 107 minus the natural log of 208 all over 31, which is negative 0.00175. That's our solution. So the natural log of 350 minus t is negative 0.00175 plus natural log of 208. So when is t equals to 360? Let's figure out when the temperature is going to be 360. Let's plug in capital T equals 360. So we end up natural log of 350 minus 160 equals negative 0.00175 t plus natural log of 208. You can just solve that using arithmetic. And the solution turns out to be t equals 52 minutes, which is about 5:30. And actually, the turkey was 162 degrees at 5:28. So this model actually worked out pretty well. So this is our solution to the differential equation. Suppose we were asked to express capital T in terms of t. Sometimes we want to do that. So we want to get capital T all by itself. To get rid of the natural log, we're going to raise e to both sides. So we have e to the natural log 350 minus t equals e to this stuff, negative 0.00175 t plus natural log 208. The right side, you can break this up. It's e to the negative 0.00175 t times e to the natural log 208. E to the natural log 208 is just plain 208. So we have 208 e to the negative 0.00175 t. That's what the right side is. And as for the left side, we know what this simplifies to. E to the x and natural log x are inverses of each other. The left side just simplifies to 350 minus t. So we have 350 minus t equals 208 e to the negative 0.00175 t. Or if you get capital T by itself, get capital T equals 350 minus 208 times e to the negative 0.00175 t. And we've expressed capital T in terms of little t. Okay, here's another example, simpler example. Solve the separable differential equation dy dx plus 2xy equals 0. Express y as a function of x. So dy dx equals negative 2xy. Again, let's get the dx on the other side. dy equals negative 2x y dx. Let's move the y to the y side. And we have dy over y equals negative 2x dx. Integrate. And we have natural log y equals negative x squared plus c. Okay? So again, this is our solution to the differential equation. We were told that we want to get y as a function of x. So let's rewrite this. Again, we raise e to both sides. E to the natural log y equals e to the negative x squared plus c. E to the natural log y is just plain y. And the right side is e to the negative x squared plus c. We can break this up by the rules of exponents. This is the same thing as e to the negative x squared times e to the c. Okay, now this step is confusing. C is just a constant. So e to the c is just a constant. And so we're going to write this as, we're just going to write, since e to the c just represents a generic constant, we're just going to write that as c. I know it's confusing to say, well, e to the c equals c. Yeah, technically that's not true, but c is just some generic constant. So e to the c is just constants. We'll just call it c. So we end up with c e to the negative x squared. And that's our solution. Y equals c e to the negative x squared.